Now we will see the change of interval from minus pi to minus pi to minus L. So far the Fourier series that was defined for functions in the interval minus pi to pi, defined in the interval minus pi to pi. Now let's see the Fourier series of functions defined in the interval minus L to L. Assume that we have a function f of x which is continuous in the interval minus L to L. Okay. And what we do is we make a substitution, x equal to Ly by pi. Okay. We make a substitution, x equal to Ly by pi. And when x equal to L, when x is L, y will be equal to pi. And when x is minus L, if you put minus L here, y will be equal to minus pi. So if you make this substitution, the function now becomes a function in y, and for x defined in the interval L to minus L to L, we have y defined in the interval minus pi to pi. Okay, so f of x is now transformed into the function capital F of y. It's a new function which is basically f of, for x we are giving Ly by pi. Okay, so Ly by pi. Okay, so f of y is now defined in the interval minus pi to pi, and its Fourier series expansion, as we all know, f of y, which is now obtained, the capital F of y, it is now a0 plus sigma n equal to 1 to infinity an cos ny plus bn sin ny. Okay, so the new function f of y, which is now defined in the interval minus pi to pi, that is now by our original definition for a function in the interval minus pi to pi, this f of y that is given by a0 plus sigma n equal to 1 to infinity an cos ny plus bn sin ny, and this f of y is small f Ly by pi. Okay, so a0, that is 1 by 2 pi integral minus pi to pi f of y dy, which is 1 by 2 pi small f Ly by pi dy. Okay, this f of y, that is actually a small f Ly by pi, that's why we have written it like this. And an is 1 by pi minus integral minus pi to pi f of y cos ny dy, which is 1 by pi f of Ly by pi cos ny dy. Okay, so an we got, bn also we can get. Okay, so bn is given by this 1 by pi integral minus pi to pi f of sin ny dy. Now in all these three equations, okay, here for a0 and for an, okay, which is given by this expression, and for bn, okay, for bn we make this substitution, x equal to Ly by pi. Okay, this substitution is made, or y we know that will be now pi x by L. So if you put y equal to pi x by L, okay, this is actually pi x by L. So when y is pi x by L. For y equal to pi, okay, for y equal to pi, for this we have x equal to L, and for y equal to minus pi we will have x equal to minus L. Okay, so f of x, that is now that is given by a0 plus combining a n cos n pi by xl. Okay, so how do we get that? Here for for here for n y we are making the substitution. Okay, this y, here this for this y we make the substitution pi x by L. Okay, here also pi x by L, pi x by L. Okay, so we will be getting f of x as equal to a0 f of x is a0 sigma n equal to 1 to infinity I n cos n pi x by L. Similarly here n equal to 1 bn sin n pi x by L. Okay, so this is our f of x. So a0, which is originally this, it now becomes this. Okay, this becomes f of x, and here we have cos n pi by xl. For dy we are giving this d pi x by L. So we get f a0 as equal to 1 by 2L minus L2 plus L f of x dx. Similarly for an we will be getting this, and for bn we will be getting this. Okay, so we just make that substitution. So we get the Fourier series corresponding to a function, see f of x here, for a function which is defined in interval minus L2 plus L as this. Okay, and we can have the a0, an, bn we can obtain. Okay, now suppose that f of x is an even function of x. Okay, then in this integral, this term, see here f of x is even, so this is odd, this part is odd. We are multiplying even with the odd function, so this will be odd, so this will be 0. Okay, this will be 0, but this will be f of x is even, f of x even cos n pi cos this function even, so we have even function. So a0 and n will be there, but bn will be 0. Okay, and f of x is now given by this, where a0 is given by this. See, 0 to L instead of minus L2 plus L we have 0 to L 2 times, 2 will get cancelled, and for an we have 2 by L this. For bn, that is 0. Now f of x is an odd function of x. Suppose that f of x is an odd function of x, then a0, an will be 0. Okay, odd function, because this will be odd, this also will be odd, so this will be 0. a0 and an will be 0 only. We will have bn, because odd function when combines with the odd function, we will get an even function. Okay, so we have a0, n0, and f of x simply sigma n equal to 1 to bn sin n pi x by L, where this bn is 2 by L, L0 to L f of x sin n pi x by L dx. Okay, so this is what we get. Then we see the complex form of Fourier series. Okay, Fourier series that can be expressed in a complex form. How do we do it? By making appropriate substitutions for cos nx and sin nx. For a function defined in the interval minus by 2 plus pi, f of x is given by a0 sigma n cos nx plus sigma n bn sin nx. We express cos nx like this, e to the power I nx plus e to the power minus I nx by 2, that we know. Sin nx can be written e to the power I nx minus e to the power minus I nx by 2i. 2i is there. Okay. So here we have 2i. Okay, 2i is there. So this is cos nx and this is the sin nx that we substitute for cos nx and sin nx. We substitute this complex form. Okay. So we have this f of x is equal to a0. an cos nx is this. Here bn sin nx is this. And we multiply both numerator and denominator by I here. So we will get I into I minus here. So minus. So f of x is given by this. So here we have e to the power I nx. Here we have e to the power I nx. So an minus ibn by 2 e to the power I nx here. And sigma n equal to an plus e to the power, here e to the power I nx coefficient an. Here e to the power I n minus I nx coefficient is bn. Sorry, ibn. So we have this an plus ibn here by 2. And this a0 is written as a0. And this term is written as n. And this term is written as c minus n. Okay, this is written as cn and this is written as c minus n. Okay. And then here for a0 I am writing c0. And here I am introducing a e to the power I 0 into x. Its value is 1. So I can add or safely add this term. So I will be getting f of x as equal to sigma n equal to minus n plus infinity cn e to the power I nx. Okay, we can express this in this form. Okay, for negative values you will have this. For positive values you will have this. Okay. For 0, you will have this term. So f of x equal to this. So this is the complex form of the Fourier series. And how do we determine the coefficients here? We multiply the above equation, this this equation. This is multiplied by the e to the power. This equation is multiplied by e to the power minus imx. So see, we are multiplying with the e to the power minus imx and integrating between the limits minus pi to pi. I will have this. The thing here is when m is different from n, as you integrate and apply the limit, you will be getting 0. And when n equal to m, since here we have my negative term and positive term, they will vanish. You will have dx here. And when you apply the limits, you will have 2 pi here. Okay, apply integration and then applying the limits, you will have 2 pi. So cm into 2 pi. So cm is 1 by 2 pi. This minus pi to plus pi e to the power minus imx dx. Okay, for m, if I substitute n, I will have this 1 by 2 pi. And I will minus pi to pi e to the power minus inx dx. So this is the coefficient. Okay, so we have the complex form of the Fourier series. This is the complex form and the coefficient is given by this. Okay, now another thing is we might be asked to find Fourier series in the interval 0 to t. This is in time. Okay, 0 to t, the t is the time period. So here the Fourier series is expressed like this: a0 sigma n equal to 1 to infinity an cos n omega t plus sigma n equal to 1 to infinity bn sin n omega t. Okay, and a0 with you can find the a0 an and bn. a0 you will get 1 by t integral 0 to t f of t dt Okay, ANS equal to 2 by t integral 0 to t f of t cos n omega t dt, and BNS equal to 2 by t integral 0 to t f of t sin n omega t dt. Okay, so Fourier series for this interval 0 to t can be